Hello guys, welcome to the video of Physiology of Hearing. In this Physiology of Hearing test we are going to know about the sound localization. Usually when a normal person hears about a binaural hearing, that is when we hear by both ears, the both sound effects will be absorbed by the brain, and we can able to localize the sound where the sound is coming from. This is known as head shadow effect. But when there is a monaural hearing, when there is only one stimulus here received by the brain, so they can't compare the intensity of sound. No sound localization will be there. Okay guys, then we need to about the role of different parts like outer ear, tympanic membrane, and the middle ear and the inner ear, to how we can able to hear. First, the in external ear there is a pinna collects the sound the help of the tragus, and their are going into the external acoustic matrix, then into the tympanic membrane. When we see the surface area of tympanic membrane, it's 90 millimeter square, but the effective vibratory area is only about 55 millimeter square. And also the surface area of step so this past tense helps in the vibration and produces helps in the production of the sound. And then there is the surface area of step size only about 3.2 millimeter square. When we compare this 55 millimeter square with 3.2, it is about 17:1 ratio. So the effective vibration will be more. Then when we see the lever ratio of the handle of malleus is about when we compare this with incus, it is about 1.3 times more. The incus is, we can keep it as x, and malleus handle of malleus can keep it as 1.3. so the lever ratio is also 1.3 is to 1. This is known as torque, the force and length. There will be more amplification of the sound. This help. So with the help of this middle ear, there is an increasing of the amplification by 22 is to 1. Okay guys, 22 times the time will be amplified, the sound will be amplified. This is known as acoustic coupling. This is known as oscillator coupling. Sorry guys, there is another process taking place in the middle ear that is known as acoustic coupling. That is whenever the sound first travels through the hits the tympanic membrane, and then it first goes into the oval window. It travels through this scala vestibuli, then comes to the scala tympani, and again it beats the round window. So the round window bulges out. Again, sometime a small sound will also this due to the oscillator coupling. First it reaches the oval window, but some sound without going to the oscillator chain, it goes and beats the round window. So this the direction the wave moves towards the scala tympani, then into the scala vestibuli, and then it strikes the footplate of stapes. So now the footplate of stapes bulges out. This process of first bulging out, second bulging out, second bulging out. So this is known as acoustic coupling. This also maintains the pressure and creates a pace difference, and also helps in amplifying the sound, guys. This is about the middle ear. Middle mechanism of two types: oscillator coupling and acoustic coupling. Then let me go into the inner ear. The inner ear, the sound waves that is first goes into the scala vestibuli, then it movement reaches the scala tympani. This scala tympani, above the scala tympani there is the basilar membrane. So the basilar membrane will be stimulated, and it activates the organ of Corti. In the organ of Corti, there are organ of Corti is the principal organ of hearing, basic unit of hearing. In the organ of Corti, there is presence of hair cells or the serocilia on hair cells in organ of Corti have tippling, guys. This is known as tippling. This is the hair cell, this is the serocilia, and within the serocilia there will be tippling will be present, which is very important in this hearing aspect. Okay, the when this fluid moves, there will be bending of the all the stereocellular. So the stereocellular will touch this, and this will touch the next one. So the stippling will be extending, so there's the presence of cation channels here. So the cation channels are activated. This leads to the movement of K plus and Ca plus 2 from scala media. That is the endolymph containing the scala media into the stereocilia. The movement of ions takes place. Okay, guys, and this creates a potential known as cochlear microphonics due to the movement of K plus ions. This is a alternate current, as the movement of the ions may produce this current. Okay, then when this channels get activated, you can see this channels are activated. Then with the help of this myosin, suddenly myosin will come downwards. So this stereocilia come back to its normal position. Myosin comes down, that it also known as the tip link, guys. Okay, guys, as I said, no, this tip link is very important. There is a syndrome known as Usher syndrome, where there is the mutation of gene encoding cadherin 23 or proto-cadherin 15. So this causes the absence of tip link. So the person will experience a sensory hearing loss along with the vision loss due to retinitis pigmentosa, and this cadherin also plays a role in their vision. Okay, guys. You can see some people are both deaf and blind. Yes, then there are 4 important potentials in the cochlea. Known as first is the cochlear, a direct current, then cochlear microphonics, summating potential, and and action potential, guys. This direct current is that can be stimulated with no acoustic stimulus. Then we seen about the cochlear microphonics, that is the current within the stereocilia, that is produced due to the movement influx of K-plex due to opening of fine channels in response to sound stimulus. This is an alternate current. This takes place in the outer hair cells, whereas this summating air potential, it takes place in the inner hair cells in response to movement of K plus ions. It has a higher latency period than cochlear microphonics, guys. The summating muscle, and then is the 8th nerve action potential. This is the action potential that is due to the done in the nerve cell. Okay, guys, it is produced only when stimulus is above hair threshold. Is a sub threshold, you can say this threshold, the stimulating threshold, and it may be also supra threshold. Then we can study about the electrocochleography. This is plotted against the summating potential versus action potential. In normal ear, this summating potential is will be less than this action potential. It is about 30%, whereas in minor disease, the minor disease is due to the abnormal amount of endolymph, which may cause vertigo. So this summating potential is 70% more than the action potential. This is a confirmatory for minor disease, and indicative is that the summating potential is more than 45% than action potential. Guys, you can see the normal graph lies. This is the action potential, this is the summating potential. This is stimulus. Summating potential is a longer latency as that action potential, but in this curve you can see the summating potential is increased, but from this curve it's about increased about 70% to 40%. This electrocochleography is a confirmatory test for minor disease, but this electrocochleography is an invasive investigation. You have to make a hole in defined membrane, so you have to perforate or not perforation, to make a hole in the membrane to place electrode on round window. Okay, guys, then we need to study about how these different frequencies are localized in cochlea. There are 2 theories. First is the place theory, and next is the this frequency wave theory. frequency wave theory or traveling wave theory, guys. According this to space theory, they said that at the base the higher frequency sound are here, and at the apex lower frequency sound are here, and it is 20 hertz is here at the apex of cochlea and 20,000 is here at the base of cochlea. The normal hearing range of about 20 to 20,000 hertz. And then we go into the traveling wave theory. For this theory, Von Beksky won Nobel Prize in Physiology or Medicine in 1961, guys. According to this theory, this is the base, is the round window. From this a long frequency, then it as goes to apex, the became lower frequency. So as the peak shift towards base, as the frequency increases, the peak shift towards base, and as the frequency decreases, shift towards apex. So higher frequency are here at the base and lower frequency are at the apex. The neural pathway is also as a frequency coded. Next we go see into the speech intensity. Intensity is nothing but the strength of the sound. It is measured in dB, or decibel in respect for the Graham Bell who discovered the telephone. Then the sound of whisper is about 30 decibel. Normal consideration is 45 to 60 decibel. Produces then noising market output is 60 decibel. Then more than 80 decibel is dangerous. As per WH guidelines, sound intensity more than 140 decibel can lead to deafness, even if there is a microsecond. This is the WHO guidelines for noise levels. The according to the Factory Workers Act 1948, for workers who are working in a mine or something, or like factories, 90 decibel for 8 hours is the maximum tolerable sound noise. But as per WHO guidelines, they asked to decrease this and change it to 85 decibel for 8 hours. But according to this, and now everywhere is about where WHO in guidelines of India, as they say, it is maximum tolerable sound is 85 decibel for 8 hours. But as the sound increases, you need to decrease the time by 5 decibels according to Indian. But according to WHO, as the 3 decibel there is increase in the sound, there will be time duration of half an hour will be reduced, whereas for India it is 5 dB. Okay. Thanks guys, let's see in the next video.